So, my name is Will. I am a fourth year mechanical engineering technology student here at RIT, and today I'll be displaying my final project for my class MCET-520, Measurement Systems and Controls. Now, the initial goal of this project was to take some random sensor that we would be given in class to measure something, quantify something, get something tangible out of whatever interactions we had with the sensor. Now, I was randomly chosen to use a piezoelectric force sensor. That's actually this little beige chip that you can see at the top of the box there. And my goal with this sensor was to measure mass. I wanted to create a scale of sorts. I wanted to measure the mass of any object that I put on there in grams, and so that's what I built the project up to be. Now, the purpose of this video is, again, to showcase the project and sort of explain to you how everything works in here, what's going on. I want to talk about the general build as a whole. I want to discuss the signal chain throughout the project, sort of the magic that's going on behind the scenes that lets me get a mass output from this literal black box. I want to talk about the calibration process, sort of what that looked like, and then I want to wrap things up by discussing some of the things that I've learned from this project as a whole. To kick things off, let's start by getting more of a top-down overview of the full project. So here you can see sort of a top-down view of the project. This is the whole box. This is kind of everything that I was working towards. Right on the top, you can see that piezoelectric sensor. It's sort of that beige chip, a little bit of glare on it. And that's what's doing all the magic here. That's what's taking our force and turning it into a readable output on the front there in grams. So right now I'm actually missing my offset block, which is why the output is negative. But you can see as I press on that sensor, I increase the value and it goes all the way up. It can read just below 300 grams at peak, and then I can drop it back down again by letting up a little bit, and it'll go all the way back down. Now, let's take a little look inside. So, inside of the box, you have a lot of stuff going on. You have the sensor at the top, you have a breadboard down in there, you have the LCD screen, you have your Arduino back there. Basically what's happening is your signals are coming in through the sensor, right? They're traveling through those yellow wires that you see, and those go down into that breadboard down there. Now, the breadboard has a voltage divider circuit as well as an inverting amplifier circuit. The voltage divider serves to take the 5-volt power source from the Arduino and turn that into a usable 1.25 volts for our sensor here. And then the amplifier is taking the changes in voltage across the sensor, usually directly from the sensor, they're in like the microvolt range, and then turning that into a difference of a full volt for the Arduino to read. So they're both pretty critical here. You can see that red wire there going into pin A0 on the Arduino. That's actually what's carrying our signal. The Arduino takes the amplified signal in, it does kind of some math in there, it does a little bit of magic honestly, and then it spits back out a proper value in grams, a proper mass output. That output, if you can see these colorful ribbon cables here, that output gets sent back to the Arduino, or sorry, back to the breadboard. It's transferred over to some different wires, and then it gets sent to the LCD screen on the front for everybody to read and see. So I'll pop this back on here. Let's see, okay. And then over here, as I mentioned, my null block is not there, but first I want to drop down my force distributor, which is basically a really fancy way of saying a super flat piece of plastic. Put that on top, make sure all the load gets evenly distributed. And then, because these sensors are very finicky, as you'll see later on in the video. Then my actual null offset, the offset block that I've been talking about, is basically just this machined flat, pretty dense hunk of steel. And so I drop that on there. So I'm gonna get it to sit nicely. There we go. And now you have the full project. So you can see again, I have to hold it in place so it doesn't fall off, but you can see I press down on the block, it gives me a force output. If it was sitting flat on the table, which you'll see that later in the video, it would be reading properly right now, but that's pretty much all there is to it. Everything comes out through this side cable here. It's all programmed, powered, and operated by my laptop. And that's about it. Okay, so now I want to dive in a little deeper and talk about some more parts of this project individually. So, this is a sketch of my circuit right here, simplified of course, but you can start to see everything that's going on. On the far left, this represents our piezo sensor, and what you'll see there listed as Vref is the voltage source that's being fed into the piezo. One interesting thing is that in the case of this circuit, that was actually a negative voltage. So, as I mentioned before, I'm using a voltage divider, which you can see down here, these three resistors, to step down 5 volts from the Arduino to 1.25 volts on the sensor. And then because I need a negative voltage here, I'm actually feeding the ground line from that power source into the sensor, and then I'm feeding the positive voltage into the non-inverting terminal of the op amp. So power is going to ground and ground is going to power because I need a negative. It's a little confusing, but it works out. Um, and then from there, going over to the right a little bit, the output from the sensor goes into the inverting terminal of the op amp. So that's this negative here, and then again, the op amp is this kind of black chip. Um, Up next, I have two components bridged across the output line back into the inverting terminal. That is RF and C1, which you can see down here is kind of this one blue capacitor, that's C1. And then these three resistors in series actually make up the RF value. I wasn't able to get one single resistor with exactly the right resistance, so I had to chain them together. But C1, the capacitor, all that's doing really is helping to smooth out a little bit of the noise in my circuit. So that's making the signal slightly cleaner, even though it wasn't perfect in the end. And then all of those resistors are what we like to call the feedback resistor. So the feedback resistor is actually what allowed me to tune the gain in my circuit. Adjusting the value of this resistor is what adjusted the voltage output from the op amp on this output terminal here. And subsequently, it's also what allowed me to select my final force range. By adjusting this resistor value, continuously applying different maximum loads on the piezo, and observing the voltage output, I was able to settle on a resistor value of about 2.2 megaohms. And this gave me my maximum mass range of 0 through 300 grams at a voltage output of 0 through 3.6 volts max. So that's kind of everything here. Up next, I want to switch over again and talk about the Arduino itself a little bit more and kind of dive into the code there. Okay, so now looking at the actual Arduino code itself, one thing I want to mention first, if you noticed in the previous pictures that you saw, I am actually using an Arduino Uno R4 board instead of kind of the, I guess what's standard nowadays, the R3. And that's because the R4 has an onboard ADC with a bit count of 14, as opposed to the standard R3 with a 10-bit ADC. And we'll get into why that's important a little later on. But to start off, let's talk about the code itself. This is kind of what makes everything happen. And going top down, you'll see that I begin by including the library that lets me control the LCD screen. And then I set the window size of my moving average filter here. And again, we'll discuss that further on. Everything from line 4 through line 14 basically is just me initializing different values. And then in the setup section here, I have one interesting part, which is setting the analog read resolution. This line is what actually lets me use all 14 bits of the ADC. And then more initialization. I'm telling the Arduino that I want it to read that input signal from the op amp on pin A0, and then I'm telling it to start up the serial monitor, and I'm telling it to start up the LCD screen. So then, looking at the loop section, this is kind of where the actual interesting stuff happens. Everything from line 25 down through 31, this is the filter itself. Essentially, what it's doing is reading all of the incoming voltage values, taking the average of 50 of them, because again, I set my window size as 50 up here, and then setting that as the first value that actually gets used. So then it moves one step over, and it repeats this process again. It takes an average, it sets that as the value. Moves one step, takes an average, sets the value, so on and so forth. Essentially, every value that you would see coming up on the LCD screen is actually an average of 50 individual readings, and that's why you see a bit of delay in the numbers that update on the screen. Now, I'll have a better example of that updating process in a second here after this slide, but most importantly for now, right below this, I want to talk about the calibration equation. this is what takes the voltage values and then actually converts them to the proper mass values in grams. It's based on a ton of calibration that I did in the lab one day. And again, I'll explain that further along in the next slide. But really, it's kind of just simple algebra. You're multiplying your voltage value by one constant value, and then you're subtracting another constant value afterwards. But figuring out exactly what those values were was admittedly a really painful process. But we got it all figured out and we're here now. It's working mostly fine. Lastly, beyond there, we have the code that prints everything to the LCD screen and the code that prints these values to the serial monitor as well. Next up, I've already discussed some of these things partially, but I want to talk about my signal chain as a whole in one concise segment, and then I'll move on and show you what the calibration process looked like. As you can see, everything starts out with the piezo sensor. That's what gave me my initial voltage values that I worked with to make everything else possible here. Those signals are taken through the process of amplification. This was already discussed a little bit, but that's the whole process that was going on with the op-amp circuit, taking small changes in voltage from the sensor and turning those into large changes in voltage on the output terminal of the chip. Next is discretization. This is everything that I talked about with the ADC earlier. The 14-bit ADC is taking in the continuous analog signal from the amplifier, and then it breaks that down into 16,348 distinct values across a range of 0 through 5 volts. And in case you were wondering, that 16,000 number is 2 to the power of 14. That's where we get all of our chunks from, so to speak. This is what gives us such a nice resolution here, at least in an ideal world where things worked the way they were supposed to. And the last step is filtering. I just covered this. I used a moving average filter to remove a ton of the noise that was caught up in there previously just from everything going on with this project as a whole. So up next we have the calibration video. This is a little bit of the calibration process. It shows you a little bit of the functionality of the circuit. As you can see, I have 100 grams on there right now. It is not quite at 100 grams. I can drop 150 grams on there. Each of these masses is 50 grams total. And now it's reading 151, which is pretty accurate. And then I drop another one on there, and it's reading 230 all of a sudden. Honestly, the variation was pretty frustrating to deal with. A lot of the time I felt like it kind of had a mind of its own. I didn't quite know what to do, and you can see how finicky it is here. If I just adjust it a little bit, it'll drop by 50 grams. This wasn't something that I was necessarily able to overcome within the given time frame, but it will be discussed in the next portion of the video, which is purely talking about calibration. Okay, so finally, the moment you've all been waiting for, calibration. Now, this may look like a mess of data and charts and all that, but I promise it all makes sense, and it was all valuably taken into account when planning out the final calibration curve for my project. So the most important part can be seen along this top row here. These were all of my upscale tests. Now what that means is that I've taken one of my weights and placed it on the sensor, recorded the value, placed another, recorded another, so on and so forth, until I hit my maximum voltage reading. I'm going from 0 all the way through 250 grams. Once I hit my max, I would then take all the weight off and start that over again. I would do another test. I did this a total of 5 times from 0 through 250 grams, and I plotted everything out over here. There we go. So you can see these are the trend lines of each individual data set, and thankfully they are all pretty linear. They are all pretty similar to one another. There's a little bit of spread. So that's good. That means that because they're not starting to fan off and go in different directions as we get to a higher mass, we don't necessarily have to worry about any issues with sensitivity error, which is good. But then we'll come over and look at what happened next. So I connected each data point to show you sort of what was happening, and now you're starting to see the source of a lot of my error. So yes, the trend lines look good. They're all pretty similar. They're close together. But when you actually look at the path that each data set is taking, you see where all of this variation is coming into play. Some of the lines were fairly linear, like the orange set here. Some of them had a weird bump in the middle. Some of them had this kind of constant curve all the way through, like the blue line. It's honestly sort of just a mess, and there wasn't a ton that I could do about that, unfortunately. But I did take each data set there, average all of the individual points together on one solid trend line, and when I did that, I had a little bit better luck. You can see the trend line there fits quite well. I have an R-squared value of 0.998, which I'm happy with. And this equation should look a little familiar. It's the same calibration equation that I used in my Arduino code. So this is what actually let me know how to correlate a given voltage value to a given mass. Next, I want to go down and talk about the second set, which is my repeatability tests. So in this case, I was taking the same mass, 0, 50, 100, so on and so forth, and I was placing that on all at once, and then I was taking it all off. So it was all on, all off, all on, all off, record the voltage every time, do that 10 times for every possible mass range that I could have. And this was the result of that data. It's a little less than ideal. You can see that in the 0 through 100 gram range, things are actually pretty acceptable. This is kind of what you would expect based on the trend lines that I showed you in the data set above. But then you get to 150 and you start to look at 200 and 250, and not nearly as nice. There is a ton of high-end repeatability error here. So basically it likes its values down in the low end, but then once you get up here, it's going to jump around on you. You're never going to be positive of what it's doing. And that's exactly what I saw when I was performing my testing. Anything past, I think it was around 140 grams, it just got painful. And so you'll see it's pretty good, pretty good, pretty good. Here it starts to spread some. Here it starts to spread a ton more. And then the green portion here starts to drop back down a little bit. But one thing that you need to consider is that I have a voltage cap of 3.6 volts. The op amp will not allow me to output a higher voltage than that. I do truly believe that if that cap wasn't there, all of those really high-end values would have gone even further, and we would have seen more spread at the 250 gram range, but sort of just working with what we got here. Lastly, I want to move over and talk about my hysteresis tests towards the bottom. Let's see if I can find that. I did 3 of these. Now, hysteresis error is the idea that you can add weight incrementally on a sensor and plot it all the way up, and then you can remove that weight incrementally as well, all the way back down. And you might, if you have this type of error, you might see a difference in those data points. It's not going to be linear. And that's kind of what I found. My first test, you can see there's just so much variation that it's kind of hard to see it come through. My second one, similar situation, you have a little bit of crossover here, but you can start to see how those data points are trending downwards on the way back in as I remove that mass. And then this one exemplifies it the best. So I start out nice and high over here, adding my mass up and up and up. I hit the top, and then when I start to remove it, the values that I get are consistently lower than the values I had in the first round. And this is my hysteresis error. So yes, the data collection process was a little grueling. Had to sit in the lab for a while to get all of this, but again, especially this first data set over here, this kind of served to help me do the calibration itself, and this is what sort of made my project functional. And then I like to say that the second set is what made me accept the fact that it's not going to be perfect, especially on the high end, and that's just kind of something I have to deal with. But overall, it wasn't too bad, and this is sort of what made everything possible. So, we've covered a lot, and I want to wrap things up finally by talking about some of my takeaways. This project was frustrating, but admittedly, it was also kind of fun. I had a good time getting to remind myself about how to work with Arduinos, and even if my implementation wasn't always perfect, I do feel like I've learned a lot of valuable things in the process of completing this. I would say that overall, the main thing that I've learned is that piezoelectric sensors make for less than ideal load cells, and you should use a strain gauge if you want to measure mass. But no, in reality, I think the biggest thing that I've learned from this is that nothing is perfect. You can design around noise all you want, but it's still always going to be there regardless of what you do. All the filters in the world and all the calibration time possible is never going to get you up to 100%, and that's okay. This was still a fantastic learning experience. In my case specifically, the error might have been worse than it was for others. I honestly wouldn't be confident in saying that this was accurate past around plus or minus 10 grams in the 0 through 200 gram range. I don't know about beyond that, but that's okay. I think that for a mechanical engineer doing what's basically an electrical engineering project, I still did a decent job. I learned a lot about amplification for the first time ever, really. I got to remind myself about how Arduinos work. I got familiar with what a signal chain even is. I learned about filtering, how to properly calibrate something, so on and so forth. Yes, this project was frustrating. Yes, I got way too familiar with what that lab room looks like that I was working in, but I still had a good time. I learned a lot, and I'm kind of proud of my little sensor box now, even if it's a bit dysfunctional. Thank you.